we have tested our program. It works almost perfectly. But you find a bug, and how do you debug that? I usually have more lectures on debugging. I don't have time in this new format of the course, but I selected one topic of, from debugging that is beautiful in many ways, and it's also very, very useful occasionally. So that's called delta debugging, and it's a cool way of having the computer debug for you. Debugging is very hard. It requires a lot of a certain kind of mindset of trying to hypothesize what's wrong, and it requires a lot of tools. So you should get good with debuggers, because then you can be a lot more productive. What's the difficulty in debugging? So often you get the bug report. Oh, my program crashed, and then immediately ask, what are you doing? Oh, I don't remember. Okay? Does it crash still? No. Okay, that's a pretty bad situation. So let's assume for now, simplify the problem a little bit. Let's assume that we can reproduce the bug reliably. So we have a software system, and we have a certain way to exercise it. Let's call it that's the input to the software, and every time we give that input, it crashes. But this input might be a very big thing. If you're writing a compiler, somebody sends you a megabyte big software program that crashes your compiler. What do you do next? It would be nice if from that big input you synthesize a much smaller input that still crashes the program reliably every time. That's the one that you probably want to run in debug mode. It's a debugger with breakpoints and all that good stuff. And then you locate the fault in the source code, and then you fix the fault. Okay? This actually may be very, very hard to fix the fault. Because you might discover that the bug is not just a small typo, it's an architectural bug. You can't just change it here, you have to kind of redo the way things communicate. We're not going to talk about that. Hopefully your architecture is clean, you don't have that problem. This is the problem that we're going to discuss today. How do you take a big reproducing scenario and make it into a small one? Let me give you an example as further concrete motivation for this. I looked at Firefox. Actually, rather, I have learned this story from Firefox developers. They get a lot of bug reports a day, every day. Sometimes Firefox sends automatically the bug report, but sometimes people give web pages. Here's this web page crashes the browser. Most of them are pretty big. And they're still grateful to get them, but you need to somehow simplify the bugs. So at some point they had more than 800 bug reports, and they were getting more bug reports in than they could actually make progress on. So they had a call out for volunteers to process the bug reports, and most common task was to simplify the reproducing scenario. And then once it's simple enough, you can debug it. You can even see that it's a duplicate of something else. So simplifying meant trying to turn these bug scenarios, these inputs, into a much smaller input that reproduces the problem. Let's now take this special case of a Firefox bug that you give it the HTML page, it crashes the browser. And actually they had such bugs. This is one of them from the early days of Firefox. There's all this mess, and whoever submitted this bug already kind of probably removed some of it, but then it kind of gave up trying to figure out what exactly in there is the problem. And it turns out, I don't know if I can see it, but after minimization, it's this. If you have a web page, on that version of Firefox, if you had a web page, you just have to select tag without an N, it would crash Firefox. Okay? You can probably imagine that this can happen. The question is, how do you go from this to this? And this is what we're going to discuss today, some cool ways of doing that. But let me ask you to think, why do you think this is good? Why do you think we want to simplify these bug reports?
suppose you're looking at whatever parses the HTML for the web page. If you have to parse 100 elements, your debugging job is going to take a long time as opposed to just one.
Right. So you probably debugging, you'll have to iteratively kind of figure out where the problem is, and stepping through the code on a large input is a lot harder than what else? What are the other advantages you might get from a smaller bug report rather than the big one?
It's easier for the humans to understand. Or
Right.
It's easier for the next person to pass it off to like another engineer or another person.
Another what?
Another person who's writing the code, and it's easier to transfer
Yes.
knowledge.
But I'll just hook on to the first thing that you said. Sometimes if the bug is so small that everything in there is relevant for the bug, then you can look at it and you can start already mentally hypothesizing what could be wrong or in what part of the code would be wrong. Because you know that if you remove this part, the bug doesn't appear anymore. So everything that's in there has to happen at once for the bug to happen. That's the definition of minimal. Okay, there's more reasons why you want minimal.
It helps you to see similarities between bugs?
Yes. Many of these 800 bugs that people filed are probably the same one. So all of the pages that had this select would crash for the same reason. There's no point in trying. You increase the priority of the bug, but you don't assign it to multiple people. And more? That's it? I think I have one more. Smaller bug reports probably make for better regression tests to keep for later, to rerun on future versions of Firefox to make sure you don't fall back into the same bug that you had before. Okay, so ease of communication, you got this. Easier debugging, you got this. This was the first one. Yeah, I got this, and you got this too. Oh, very good score. Okay, so how? Let's try to step back a little bit from Firefox, because we want something that's more general. So in general, imagine that you have a program that deterministically fails on some input. And this input can take many forms. So let me pause here and point out that the technique I'm going to teach you has many uses, but most of them rely on some imagination on your part to see how to bridge the technique, which is in the end going to be an algorithm, with your actual problem. Okay? And one of that is to take this input and think of it in a way that makes sense for delta debugging. So for example, the input might be a sequence of API calls to a module. So somebody says, I called your module, I made these 300 calls, and it crashes. So the crash happens on the last one I made, but perhaps a subset of those 300 that came before are sufficient to find the bug. Or if you're a compiler writer, your input is a text file. Okay? It's a big one. Or a set of numbers for a sorting routine, or a set of web requests for a web service that creates something bad. So what delta debugging will try to solve is to find the smallest subset of the input for which the program still has the same failure. It's important subset, it's important same. Subset is important in an interesting way. You want a smaller input. You want a fraction of the original input. But I say subset here, and many of the examples have sequence there. Probably even the sequence matters as the input for the sorting, and maybe the sequence of web requests. So one very common trick that you do in delta debugging to turn a sequence into a subset, you take every element of the input and you give it a number, an index in the sequence. Okay? And then you say, my input is the set of indices of these events that constitute my the real input. So this is the set that you're going to minimize. And from this, you're going to find out 31 and 87. This is the smallest subset of the inputs that causes the problem. But because I'm working with indices, I'm retaining their relative order. This is the main point I'm trying to make. So the input is really a sequence, and our algorithm works with minimizing sets that whatever subset of the inputs you are retaining, they have to retain the same relative order. Keep them in the same sequential order. Any other question? Is this clear? Okay. So how would you solve this problem? I'm sure you have at least an idea, and you might actually come very close to delta debugging. So I give you a long sequence of events that causes a problem. I want you to find a subsequence of those events, or a subset of the indices of those events that causes the same problem. The answer is easier than you probably think. Okay, so that was it.
Run it on pieces.
Run it on pieces and see which one. Okay, how do you pick the pieces?
Cleverly.
Okay, so that function I don't have in my programming language, like cleverly picks sequences. So what would be a clever way? I'm sure you've seen this. What if I give you this web page that crashes the browser, and I tell you that there's one particular character in there that crashes the browser?
That's half of it.
How is that called?
Huh?
How is that called, that strategy? Test half of it.
It's kind of like a binary thing.
It's a binary search. That's what I'm getting at. So whoever named delta debugging, if they put the binary name in it, in the name of the technique, would have helped a lot of people like you. I'll show you. Binary search is not the whole solution here. But before I go into binary search, I need to really clarify some things. This algorithm is applicable when certain assumptions hold. The first assumption that we're going to make is that every subset of the input, let's say that there's a set of input elements, I, capital I, and I'll be using this letter to mark my set of inputs. Every subset of that set I, if I construct an input based on that subset and give it to my program, it will either fail in the same way, reproduce the failure of interest, and I'll mark that as an X throughout my slides, or not, and I mark that as a success. Okay? So essentially, every test that I run, no matter how strangely I pick this subset of input, will either crash the Firefox in the same place, or not crash Firefox in the same place. But this may mean different things. This success may mean that your program doesn't even run. Okay, imagine a compiler. You give it a well-formed Java program, it crashes. If you give it half of that Java source file, it's not going to pass the type checker. It's not going to get to the portion that crashes. I call that a success, meaning you have not found the crash that you're looking for. Okay, is that clear? It's a little bit.
Is there an example?
Say it again.
Is there an example?
Yes, you take a Java compiler. It's the example I just gave. So you take a Java compiler that crashes, let's say, when there's a while statement in the program. So it's a kind of compiler that students write in the 164. If you take a Java program that has a while, the compiler crashes. If you take the first half of that text file, simply cutting the second half without paying attention to the Java syntax, if you give it to the same Java compiler, it's going to probably not get to the crashing part. It's going to fail into the parsing or somewhere else. So I call that a success. If, however, you somehow pick from that big Java program one that has a while, a smaller one that has a while, that's going to pass the type checker. It's going to get to my crash. That I call a failure. I'm reproducing the failure. So I'm reproducing a specific failure. Everything else I call not interesting, success, as far as. So maybe this should be reversed, but this is how the algorithm is presented in the literature. And I need to add two more simplifying assumptions one of which we will simplify in the second half of the lecture. But for now, I want to show you the simpler algorithm. So I'm going to say that for now, we're interested in inputs that have the property that one single element of that input is responsible for the crash. Okay? So the minimal set is of size 1. Okay? And then I'm going to have this assumption of monotonicity. This is one that we cannot get, we cannot eliminate it yet. So let's explain what it is. There's one element of the input that crashes, that results in the crash. And no matter how much other stuff I add with it, it still results in the same crash. So this is called monotonicity. A particular input results in the crashing behavior no matter how much stuff I add to it. If I keep adding to it more inputs around it, it still results in the same crash. Not all problems have this property, but okay. Here's an example of a non-monotonic example. Let's say that you have a compiler bug that crashes if the program uses if, unless it also uses plus plus. Okay, this unless it's a kind of negation. Negation typically, if you know set theory, negation kind of damages, breaks monotonicity. So what does this mean? If you have a program that has an if but no plus plus in it, it will crash. The moment you add a plus plus, it masks the failure. Okay? So essentially, monotonicity means failures cannot be masked by additional input. So this is the case, for example, if let me give you an example. You have a very simple web service that doesn't remember any state from previous requests. You have a sequence of 300 requests, and the last one crashes. Then probably the last one is the one that crashes, no matter what came before. So the minimal set is just a set of size 1. Okay? Similarly, if you have a sorting routine that crashes as long as you have not a number as one of the elements of the input array. No matter what else you have in the array, it crashes. So then you can imagine a search that will narrow down to an array of one element and not a number. So that's monotonicity. Many problems are monotonic. So what do you do here? Well, here you can actually use binary search. With these simplifying assumptions, binary search will work. So you take your input, you include everything in the input, you run it, you find your failure. This is actually the premise of the whole algorithm. Given the whole input, you have the failure. Then you run the algorithm on half of the input, you still have the failure. It means that you need to just zoom in here. You don't care about this stuff because you were able to reproduce the failure on a smaller input. Keep doing this, and as long as you keep getting failure, you can completely ignore the rest of the part. So this is the easy part. But now you get success here. Well, because of our assumption, running this resulted in failure. There's one element in here that results in failure. It cannot be in here, because if it weren't here, because of monotonicity, I would have failure now. As long as my problem element is in the set that I'm considering, it's still failure. So it's here, and in fact it fails, and you keep zooming in until you get to a failure of size 1. And that's smaller than that you can't do. So it's really binary search. But it's binary search where the kind of property that you're looking for is whether it fails or not. So you repeatedly run your program with smaller and smaller inputs, and all the smarts is how you pick the input. So now I want to formalize what I showed you here. You really have to pay attention to this because this slide has subscripts, okay? So there's detail here that matters. This is the first version of the algorithm. We're going to have a second version that's actually a little bit trickier. So this is still kind of warm up. Whenever I have tricky code, I like to think of an invariant that I'm maintaining. So I know you haven't learned this kind of stuff. Have you learned in programming variants, looping variants, in 61A maybe? No?
Security a little bit.
In security a little bit. In what?
61B.
61B. Okay. It's a very, very powerful programming technique that helps you keep track of your work and find mistakes. So essentially, I'm going to define an algorithm called DD, or delta debugging, and it takes a set of inputs. And here's the invariant. As long as I invoke this algorithm with a set of inputs on which my program fails, which I'm going to write like this, given this set of inputs results in failure, then the algorithm will eventually return and find one of these elements in the inputs that still makes the program fail. Okay? But this algorithm is only guaranteed to work if you invoke it with a set of inputs that fail. So the first thing you do is going to be a recursive algorithm. So the base case is when the input set is of size 1, you're done. Because of the invariant. You know that this set, which is of size 1, fails. You need to find the set of size 1. You're done, and it's guaranteed that I1 fails. If the set is more than 1, you split it into two halves. I1 is the first half of the inputs. I2 is the second half of the inputs. You test the first set of inputs. You run your program on first set of inputs, and let's say you're lucky. It fails. What does this mean?
Look into the
I need to look into I1. So I'm going to call DD of I1. But every time you call the recursive function, you have to check the invariant to make sure you're not making a mistake. And DD is legal to be called as long as this is a failing set, which is exactly what we just checked. So that's fine. Otherwise it means I1 is a success. What are you doing? DDI2. But before, you should really verify that running the program on I2 fails. This kind of makes it legitimate to call DD of I2. For our version of the algorithm, this is always going to succeed. Can you tell me which of the assumptions that we've made ensures that the program will indeed fail on I2? Monotonicity, along with this property. So, what does monotonicity tell us? And also the assumption that there's only one failure. We know there's one failure among these, and these all fail. We have cut the program in two, the input in two, and I1 succeeds. Because of monotonicity, the buggy input cannot be in I1. It's important. So therefore, it must be in I2. And because it's in I2 and it cannot be masked, I2 will fail. Okay? So you see, it's binary search, but in binary search, you just use this less or equal property. Less or equal property has important properties like transitivity and such that you take advantage of implicitly when you write binary search. Here, you're doing binary search based on these tests. And if you don't have monotonicity, binary search is not going to find your input. Okay? Any questions about this?
Is the 3187 problem that you identified on the board possible to find?
No,
using that?
not this algorithm, because this algorithm only works when the problem can be reproduced with one input. It's searching for one, a set of size 1. So, other questions? Let's try this out. Although I suspect you understand how it works. So here's my example. Assume that you have 8 inputs to your program, and by our assumption, if you give all the inputs to the program crashes, let's say. It reproduces whatever failure you're looking for. Let's say that we know we're an oracle, and we kind of know ahead of time that 7 is the one causing the problem. But our algorithm doesn't. So let's see how the algorithm will fail. And this problem is it meets assumption number 1, meaning no matter what subset of that you give to the program, either it crashes or not. It meets the assumption that the failure is reproduced by only one input because it's only 7. And it meets monotonicity because as long as 7 is in the subset that you give the program, it crashes. That's monotonicity. It cannot be that 7, something else kind of masks 7 and makes the program not crash. As long as 7 is there, it crashes. So you take the first half, and because 7 is not there, it passes. And second half, because 7 isn't there, fails. So now you zoom in here, you completely forget about this first half. You take the first half of this, passes, 7 is not in there, it fails, 7 is in there. Okay? Completely forget about everything else, so now you run it on 7, it fails, 7 is of length 1, you're done. Okay? This algorithm, so you identified 7 and you're done. This algorithm would have worked if there are multiple single failures in the set. It will have found one of them. Okay? There could be several things. Like if your compiler crashes as long as you have a while statement, no matter which of the whiles you pick, in the end, it will still crash the program. It still meets the assumptions. Any questions? No questions? Okay. Yes, question.
So what happens if the bug is a result of like several elements?
Yeah, that's the second half of the lecture. That's where it becomes interesting. But, so this seems so simplistic, so naive, so obvious maybe, that you think, when is it useful? I found several uses of this in my programming career. This is not something you use, I want to point out, it's not something you implement for every project that you build. But for projects where you smell that they might have this kind of problem of huge input sets that fail that you need to minimize, then you immediately look for monotonicity, you look for what is the input, how do you coach it as a delta debugging problem. So for the next 15 minutes or so, we're going to look at one concrete problem that I had. And I hope to, this is not an academic exercise, I actually had this in code that I wrote for Conviva, actually, as it happens, a few years ago. But it requires a little bit of background. So the goal there was we were writing programs in Lua. Do you know about Lua? Yeah. Right? So Lua, it's a mini language that people like to put to embed into systems. Like many game engines, you can program the behavior of sprites in Lua because the game engine executes Lua internally. Some databases have Lua support, like the Redis database, if you've heard of it. You can upload Lua to the database server so that it runs very fast in the database without you having to go back and forth. Anyway, Lua we use because Microsoft Xbox games are programmable in Lua. I mean, the game is written in C++, but it's written to be extensible for people to write plugins, make the games do more fun stuff. And that extensibility is doable in Lua. And Conviva came in and wanted to build one of these extensions for monitoring, not the game, these were video applications like ESPN and HBO. So we had to program in Lua. But these Lua programs, they have the problem, like JavaScript, that you don't compile them. You give the source code to whoever needs to execute it. So we didn't want to leak out, the smarts of our algorithms. So I wrote an obfuscator. An obfuscator, which actually was a special case on an obfuscator, it was really a minifier. Have you used minifiers for JavaScript? Okay, it's a tool that takes your program and converts it into an equivalent program with the same behavior, except all the names have been rewritten to short, typically 2-character, unintelligible names. Okay, so just to give you an example, this is a Lua program. You don't need to understand what it does, but it has some keywords, local function, the parentheses are important, if, then keywords, return true are keywords, but ender is a name of a variable. LuaQL is a name of a function. And if you take all of these names and rename them to something like ender becomes AL, Lua QL becomes PY, it's harder for people to understand what you're doing. And actually it becomes quite hard for a large program because the names are important. So I wrote a compiler that was taking in this Lua program. It was recognizing things that cannot be changed, should not be changed. And everything else, it was renaming systematically. So if a variable name occurs in several places, you have to rename it to the same new variable name, and then the program should still run. This is very important. The resulting code should have the same behavior. And but I had a bug. Actually, I had many bugs initially in my Lua obfuscator. And the bugs were of the same kind of nature. I was forgetting a special name that should not be obfuscated. These are very obvious, but there are other names like, I think I have it on the next slide. There were all sorts of libraries that my programs was using, and I was sometimes rewriting the right keyword. And then, because it's not a keyword in a language, it's a name of a library function. And then when my program got there, instead of calling right, it would try to call something. And you get this error saying, attempt to call up value GF, which was really right. And this is the tradeback. Everything is on line 1 because I removed the new lines so that the program is all one line. And it's in these functions, okay? And it's really a pain to debug, okay? And this is a huge program. So there's a bug in my obfuscator. It shows up in a strange way because I take this big program, I put it in my obfuscator, I get out this mess, I run the mess, and it fails like this. So I had the idea to use delta debugging. But it's not obvious how you use delta debugging for this. So here's what I did. So first, I had a lot of automated tests for my Lua code. Because Cont was writing this product that had this feature, and we wrote tests for that product. And now we're putting in obfuscated Lua code to run those tests. And the tests would pass if the code is not obfuscated, and tests would fail if the code is obfuscated. Then my assumption was that there is at least one identifier that I'm obfuscating when I shouldn't. But I don't know which one. I had collected the list of 100 identifiers, and I was missing the 101st. And so I have changed my obfuscator to be able to tell it to obfuscate only a range of identifiers from A to L, and then M to Z, and then so on. Okay? With that, so I've changed my tool to get it ready for delta debugging. With that, I wrote a delta debugger that was repeatedly obfuscating the program, passing in a smaller and smaller range of identifiers to be obfuscated. And my hope was that one of them is the cause. And it's monotonic, I was hoping, because if I obfuscate the return keyword, it doesn't matter what else I obfuscate, what else other than the return I have in my code will still fail. Okay? And so I sat down, I wrote the delta debugger, and I'm going to actually switch gears now and show it to you a little bit. Sorry, I should have prepared this. You actually have my obfuscator so the lecture materials has a link to this tarball that has this, so you can actually use this in the comfort of your home. This is an obfuscator both for JavaScript and Lua, because I did the same trick for JavaScript. And notice I have these reserved names. It's just a list of names that my obfuscator will not obfuscate. It will obfuscate everything else. And I just planted a bug in here. Select is an identifier that should not be obfuscated in Lua programs. And let's say that I mistyped it. I put select A, which means that select will be obfuscated. Okay, so Okay. Let me actually open another file. Now there's a README file. And there should be a README file. Okay, so now I needed to demonstrate it to you. So I couldn't use Conviva's Lua program because it only runs on a simulator of an Xbox. So I went online to find some Lua program that's big enough that I could obfuscate and show that it doesn't work. And what I found is a Lua interpreter written in Lua. It's just a toy. Somebody wrote a Lua interpreter in Lua. Okay, and this is Lua int here. So, but first, if I run this on at the terminal, this is simply invoking Lua and passing it. This program says local v. This defines a local variable 1 plus 3 io.write v times 3. So this should be printing what? 12. Okay, and this is using the built-in Lua interpreter that I installed on my Mac. And you can also my Lua int.lua. This will load this program and run this program on this input. So this time I'm going to be using Lua to run a Lua interpreter that prints 12. Okay, and I can also run make clean. Make make build. Make build obfuscate equal 1. So I run my obfuscator. It produced this build. This is the obfuscated Lua program. This is the obfuscated version of the interpreter. And now I'm going to run this, and I hope, demos have a way of not working when you need them, but I'm going to load my Lua interpreter and pass this, and as I promised, you get this. In fact, I think I might have copied this in the slide, except that this time I'm not obfuscated the line number, so this makes it a little bit easier to find. Or Python delta debug. Okay, so it said select. As long as you have select in the program's going to crash. So it found the one keyword that it doesn't. And here's how it works. It's essentially the algorithm that I described. Let's say this is in the middle of the algorithm. It said something in between read and status. So I should say, first thing, I collect all the identifiers from the initial program, and that's my set of inputs. And then I start doing binary search in that set. And as long as something between read and status, I call my obfuscator. I'm passing it this argument, obfuscate range read status. And it will only obfuscate identifiers between read and status unless they are in the table of reserved identifiers. And then I run my program. And if it crashes, like it did here, it may crash with slightly different stack trace. You see here, tuple is not do call, do string. These are not obfuscated, but it still crashes. Then I'm actually splitting read and status, trying first half of read status. And so it's from read to S, and so on. Okay? This finished very fast. In real life at Conviva, one of these runs takes a few minutes because it's an Xbox simulator. So you really have to go get lunch. But the cool thing is that after an hour, 2, 3, overnight, it comes back with this priceless piece of information. I found in the haystack, this needle. It's really cool. And all the engineers who work on this kind of stuff use it, and they're all amazed that it works. But now you know how it works. Any questions about this? Is this cool? It is cool. I was so happy to not have to do the binary search by myself. And I've used it in other occasions, equally time-saving occasions. But let's take a break now. And for the second half of the lecture, I'll show you the more complicated version of the algorithm, where you're not so lucky that just one piece of the input causes the problem. I do have a puzzle for you. Demo now, that happened. Okay, so the version of delta debugging that we saw, it's somewhat naive. The tricky part is that it's binary search, but not with this simple numeric computation that's transitive and all that. So you have to really pay attention to monotonicity and those things. In many cases in practice, it's not enough, although there are cases when it is. And I showed you obfuscation when it worked. For example, the bug that I used at the beginning of the lecture with the select. Okay? If you take the view that the set of inputs are individual characters, and the input is a sequence of characters that makes up the HTML page, then you need all of the select and the two brackets to create the bug. Any single character from there would not do it. So you need something more than the version 1. And that's actually true in general. So let's review our assumptions. And I'm going, monotonicity, I tell you from now on, we're still going to keep. I'm going to relax the assumption that the bug is reproduced by a single element. So I want to allow bugs that are reproduced minimally by a subset of elements, not this singleton necessarily. So the previous algorithm used this assumption that if the first half along with the second half fails, which was the input assumptions, then either the failure is in I1, in which case I2 succeeds, or the failure is in I2, in which case I1 fails. Okay? So this is because of the fact that there's a single bug, it has to be in I1 or I2, and there's monotonicity, meaning that you cannot hide it. So it's going to pop up. So consider a sorting function that sometimes returns an unsorted array. You wrote it, you tried it on 10 examples, very small. Somebody tries on a huge example, and it returns an array that's out of order. The question is, what is the smallest example in which the same bug shows up? It's probably not going to be a singleton array, because a singleton array is sorted already. So that's another motivation where you need. Okay, so the assumptions, I'm going to keep the first one, meaning every subset of my input makes sense. Either reproduces the bug I'm after, or it doesn't, as before. I'm going to change this, and I'm going to change this single element of the input to a subset of input elements. But I'm going to keep monotonicity. This means that you have your minimal subset that reproduces your failure. It will still reproduce the failure if you add other things around it, as long as you keep all of the subset elements together. Okay? Questions? It's clear where we are? So before we go into the algorithm, how would you actually approach it? So we start like before. You partition the input into two halves, I1 and I2, and you try the first half. If you're lucky and I1 fails, the first half fails, then it means that everything you need to reproduce the failure is inside I1. You go recurse inside I1, and it's like before. Otherwise, I1 succeeds. Maybe you need to try that I2 fails, whether I2 fails. And if I2 fails, it's the same situation, symmetric, so you recurse in I2. So notice that in the version 1 of the algorithm, either one of these two will happen. But now, it may happen that both of them succeed. Why? Because let's say, going back to the Firefox example, there's this select statement. Let's say that you are unlucky and you cut the input in half such that the first half of select is in input 1 and the second half is in input 2. Either one of those given to Firefox will do something but will not crash because it doesn't have all of select to crash. Okay? So you are in this situation. Essentially, by relaxing our assumptions, we have added one other possibility to the algorithm, and we have to deal with it. So when this happens, you've tried both I1 and I2, and you cannot reproduce the failure. Then you know that your failure, it's either it's reproduced by some part of I1 with some part of I2. Okay? So I think this is just iterating the same thing. So by monotonicity, if I1 succeeds and I2 succeeds, it means that there's no subset inside I1 that fails. Because if there was, by monotonicity, the whole I1 would still fail. And there's no subset of I2 that fails. It means that the subset that fails in I1 plus I2 must be partly in I1, partly in I2. Okay? So the failure must be a combination of elements from I1 and I2. You get this from monotonicity. Monotonicity is still this is called interference. And really, the way in which delta debugging differs from binary search is in dealing with interference. They have a very cute trick or algorithm there. Okay, so bear with me here, because if you get this, then you get essentially the second half of delta debugging. So consider that I1, the first half, succeeds, but the whole set, I1 plus I2, fails. What we're going to do is we're going to search inside I2 first. And we're going to search for the minimal subset of I2 such that along with I1 fails. You know that there's something inside I1 and something inside I2 that make up your failure. So you're carrying for now all of I1 with you, and you keep recursing in the second half, always testing it together with I1 until you find the minimal part of I2, let's call it D2, that fails. So any one thing, if you throw out of D2, this is not true anymore.
Does this mean like this algorithm is exponential?
No.
Like the set of all subsets of I2?
No. Let's wait a little bit. We can come back to that. Okay? So once you found D2, you know that all elements in D2 are necessary for failure, along with some elements from I1. So now you kind of turn the table around, and you consider I1 plus D2. You know that this fails, so you're looking for a subset of I1, a smaller subset of I1, that this still fails. And that subset D1 gives you, this gives you the minimal set. Okay? So you split the input in half, you test each half, you know that there's some part of the first half, some part of the second half. So first you find the smallest part of the second half that along with the first half fails. And then you find the smallest part of the first half that is needed, and those two together are minimal. And this works amazingly well, actually. So here I'm getting PowerPoint issues. Okay. So consider, before going to the algorithm, I'll first run through the example. So now we still have 8 elements, but now the bug shows up when 3, 5, and 7 are together, even if there's other stuff around them. But they have to be all 3 present. So you start optimistically. First half, you run. This is not gonna crash because 5 and 7 are not there. Take the second half, it's not gonna crash because 3 is not in your input. You immediately know that you have interference because you know that the whole thing together crashes. So you know that there's some part of this and some part of this that are needed. At least one from here, at least one from here. This is important knowledge. So you're gonna zoom in inside that one. But while you search, doing binary search in the second half, you carry with you the first half. Because you know there's something in there that's definitely needed. And so you take the first half, this doesn't fail because 7 is not part of it. And now you're doing the second half, always carrying this part. This is also going to succeed or not crash. So what do you know now? You know that there is something from here, at least one from here. You know that there's at least one from here and at least one from here. This is important, right? You knew that there was at least one from this 4. If there's only one, it would have shown here or here, but it didn't. So it means it's a little bit of both. So now I'm going to zoom in to here. But I need to carry this part because I know something from here is needed. I need to carry this part because I know something from here is needed. And I'm going to split this. I'm going to do binary search into 7 and 8. And now once I get to 7, because I have 357, my crash is going to appear. And I know for sure that 7 is one. Because I know there's at least one from here, at least one from here, and at least one from here. And well, I reduced this to 7, so it must be 7. So I found one of my elements. And now I need to go search among these. I found the one in here. So I carry these because I know one is needed. I carry this because I know 7 is the one from 7, 8. And I do binary search in here. I pick 5 first. The crash appears because I have 357. I know 5 is it from among 5, 6. Then I carry the 5 and 7 because I know they are needed. And I'm going to search what is needed from here. At least one. In the first half, no failure. Second half, I get my failure. So I know that there's at least one from this that's needed. Then once I pick this, I'm done. I'm done because I know 5 is needed, 7 is needed, at least one from 3, 4 is needed. I found 3, so I'm done. Okay, is this clear? Is it clear? Okay. What's still tricky is to write the algorithm from this. I mean, you may think that it's easy, but well, actually, let me show another example. Yes, this is the Firefox example, and you'll see such a dumb algorithm in some sense. An algorithm that doesn't understand HTML will find out the bug by constructing eventually a well-formed HTML program that crashes. So you start with this input, and as long as you have the sequence of these characters in the input, it crashes. Even if you have other things inside there. So it starts with this, you just cut it in half. This is ill-formed HTML. The algorithm doesn't care. It gives it to the browser doesn't crash. In fact, probably aborts way before the crash. Then you do this, it still doesn't crash. It's not well-formed input. So then it starts pick this and starts narrowing down what is needed from this half. But notice that it fails here because you have select and the close tab. This 5 still kind of doesn't hide the crash. And eventually it found that this is what's needed from this second half. And then it goes and does search on the first half. This is the first half of select, the second half, always carrying with it the other part that is known to be needed. So you keep having interference and keep going and finding one character at a time. And eventually you'll find the exact set of characters. So this is actually part of the beauty of delta debugging because it has this kind of way to iterate and recover if you made the wrong decision. You can use a dumb algorithm to minimize C programs, Java programs, HTML, pretty much any sequence of input, as long as it's monotonic. And as long as, of course, it doesn't take too long to do one of these trials. Okay, so now we get into the hardest technical part of the lecture, which is really trying to describe this algorithm formally. So the way this algorithm works is it takes 2 inputs. it takes a set of inputs, two sets of inputs, with the following property. I by itself, the first argument, if passed to the program, does not produce the bug. The first argument plus the second argument together produce the bug. And the goal, the return of this function is the smallest set among the second argument that along with the first one still produces the bug. So this version of the algorithm is going to keep this I constant and it's going to recurse inside here to try to find the smallest set that with I produces the bug. Okay? And this is crucial to understand that this makes sense, that this produces what you want, because once you have this invariant, we're going to be able to check our work. Everything else is going to kind of fall into place. What do you think? I already told you that I'm going to recurse inside here. What do you think is the base case, the termination condition? The first thing I'm going to check. Now.
You could do that thing, the empty set, just return I.
But this, okay, this thing cannot be the empty set. Why? Because I know I succeeds, and I know I plus these fails. So these must be something. It cannot be empty. Okay?
So there's one of them.
Okay, okay. So if this is a set of one elements, then I'm done. I found my smallest subset of that fails. Okay? And I return that subset. So this means that I plus I1 produces a failure. And then presumably I will then go and try to find the failure inside I2. But we're not done. This is just one if. What if the set is bigger than 1? Then I split this set into two halves, from I1 to I n over 2, and this one. But notice that I1 now is my set I union half of my input, and I2 is I, the second half of the input. Why am I doing it like this? Because I know that something from I is needed in the failure. So I'm always carrying I with me when I'm testing. And I test the program on I1. If I get a failure, well, what do I know? I know that I by itself succeeds, because that's from there. And I know that I plus this half fails. This means that it's legitimate to call delta debugging to narrow down this half. And notice how I'm meeting my invariant. I succeeds, I plus this fails. Just tested it here. Okay? It's easy to get lost in these if you don't remember the invariant. What do you think I would do next? So I'm done with this case. It recurses and eventually hopefully it'll terminate. What should I do next if I1 succeeds? I have to test I2. And again, the easy case is when I'm reproducing my failure. If I2 reproduces the failure, I do the same symmetric thing as here. I take I1 with the second half. And the invariant holds because I1 succeeds by itself. I1 plus this fails. I've just verified it. What case is left? Splitting this part, okay? So the case that's left is that I1 succeeds and I2 succeeds. Both of these succeed, which means that I need something from I need something from here, and I need something from here to reproduce my failure. So this is where it becomes tricky. I know that I1 succeeds, and I'm going to recurse into this second half to find the minimal set of my elements in the second half that along with I1 reproduces the failure. But it's crucial here what you put. It's not I, it's not I2, it's I1. And it's easy to get lost unless you remember your invariant. So the invariant, this is legal if I1 succeeds. Well, you know that if it didn't succeed, you would have gone there. You know that I1 plus this fails. Why?
I plus
it's this. I1 plus the second half, it's I plus all of them. So you know that this fails. Okay, so visually, what is happening is you have I, and you have this is the set of I1 to IN. And you call delta debugging with this first argument and the second argument. And this means that I1 by itself succeeds, but there's something in it. I by itself succeeds, there's something in it that you need. And you need to find what are the smallest subset of here. So you run this test first. This is I1. It's I plus the first half, and this succeeds. Then you run I2. And if you're unlucky, this succeeds too. This means that there's something in here, there's something in here, and in here that all together reproduce the field. Because this is the only case that you could reproduce. And now what you do next is you take I1 and you take, you call DD on all of these and this. You know that all together they fail because it's like before. You know that this succeeds because you verify that. And you need to find the smallest part of this. So you're recursing into the second half. And B2 is some part of this that along with I1 fails. So at the end of DD, you're getting I1 and then maybe some part of this. This is D2. And you know that this fails. This is the result. D2 is going to be the result of this invocation of delta debugging. So now you keep this aside. This is part of the result that you found. You need to find the smallest subset of that, and then we'll find the smallest subset there. So to find the smallest subset of this, I'm going to invoke D1. I'm going to keep D2, and I'm going to pass this to find the smallest subset in this that fails. Okay? And once I find the smallest subset from here, I return D1 union D2.
So what you call DD on D2, first on?
There's a bug. In the algorithm. Very easy to make such bugs. The bug is in the last call to DB. Okay? I'm going to let him try to explain.
The first argument should be I union D2.
Which one?
I union D2.
This one. What do you say?
I was thinking you don't really know that D2 is successful, do you?
It's a good one, but probably does because you know that this by itself doesn't fail, it needs I1. So any subset of it should not fail by itself, it needs I1. It's not so obvious, but I think D2 succeeds with the assumptions of the algorithm. You're close. What are you thinking?
The second argument should be I1.
This one should be I1? Well, not quite, because we're trying to narrow down this part. And we kind of split it in halves. We looked at the second half, so we should look at the first half now. So it kind of makes sense that we're doing the two halves now.
Well, the invariant is broken.
The invariant is broken. Because what I know that this succeeds, I just verified it here. I know that this plus this fails, and I need to recurse into this. So now this is going to become the second argument, because I need to recurse in there. But I need to give the first argument something that along with this fails. And I've given D2. So I'm giving D2 as the first argument and this as the second argument. And these together don't fail. So I have to give I union D2. So the first, the last call to DD should be exactly as you said it. DD I union D2, and then recurse in this. You have to carry the I with you because you know that's important. You have to carry the D2 because you just found it's important. And then you recurse in this. Once you're done, D1 union D2 is, yes.
What subset is the last one that you're working?
What subset, this part?
In the last line that you just wrote?
This one?
Yeah.
This is a replacement for this. This should be I union D2. Because if you call it like this, this part of the invariant is not true. It's not true that D along with that fails. You also need I. Because D comes from here, from this part. This comes from I1. You need the other part of I1, which is I. Okay? So you see, I mean, delta debugging, but not quite, and it's actually quite tricky to write. Other questions about this algorithm? There's a question about running time. It's not, you don't really consider all subsets of it. It could be linear in the worst case, but in practice, it's actually much better. What else I want to say? For my obfuscation problem, I knew I might have to implement this. But I said, well, I'll try the easy one first. I'll find all of my one element bugs. And that was enough. I never got to implement this for the obfuscator example. For other examples, you may have to do it. So if you still have the single, the special case that a single element reproduces the failure, then this runs in logarithmic number of trials over tens. Okay? But this assumes that running your program doesn't depend very much on how big that input set is, and that's not always true. So let me show you quickly one more example. That's actually pretty cool. It's an actual thing that happened. So somebody submitted this program to the GCC bug list saying that if you run this on GCC 295.2 with all optimizations turned on, the compiler crashes. And the compiler should never crash. So there's a bug. And this is already a small program, so the programmer probably worked quite a bit to remove comments, remove all other stuff. And this was fixed with delta debugging, a dumb one that just cuts the file in two, whatever that falls. It gives it to the compiler, see if it crashes, and then keeps trying. And here's a graph of how it goes. This is the number of tests executed. And this is the size of the program. Initially, it starts at 755. So you see how it goes to half, and then it runs multiple attempts trying to figure out even a program that a small program that reproduces the bug. So this is pretty classic in delta debugging. It has times when it doesn't make progress because the way it happens to be cutting the program just doesn't make sense. It doesn't hit the bug. But then at some point it just hits the jackpot and suddenly moves to a smaller program. And so these kind of levels are the smallest programs so far that has been found to. And then here it starts to make progress almost with every run. And then it ends up with a program, I forgot how big that is, but we can see it here. This is what it produces. So this is a one minimal case. Every character you take out, it doesn't crash anymore. Notice how the function name from mod has been reduced to t. That's enough to reproduce the bug. Double, well, it kept it all because it was a keyword. If you try to remove anything of that, it doesn't type check. And it's interesting that, you start to remove multiplications, additions, parentheses, it tried everything. And this is the smallest, even white spaces are not. So this program actually is not semantically equivalent to the original program. But that's not what we're looking for. This program is equivalent from the point of view of crashing GCC. And you give it a developer and say, anything you remove from here is not going to crash anymore. So that immediately says, oh, wow, we need this +1 there. If you don't have this +0, it doesn't crash. So what in my compiler is so sensitive to a +0? And anyway, the story continues. I'm kind of running out of time. But the next step is GCC has 30, that version had 30 optimizations. And you can do a binary search on which subset of optimization, and which you can turn on and off by command line parameters. So you do a quick binary search of which one of those optimizations, if enabled. So these are the optimizations, and so on and so on. So it turns on that if you disable this optimization, force ADBR, which I don't remember what it does, that's the one with the problem. So now you send this bug report. You send a little one-liner program. It says, turn on optimizations, but turn off. If you turn this off, the problem disappears. So this is a very much more valuable bug report that you can actually start working on. Okay? So there's a couple more slides. The conclusion being that this is a great tool, but it does require some imagination on your end to take your problem and phrase it in terms of subsets of inputs. And you've noticed from my example, sometimes I had to change my tool to give it the ability, like to control which subset of identifiers to obfuscate. So it's not an automatic thing that you can use, but when you can, it improves things a lot. And the other thing I should notice, delta debugging is an algorithm, but it's not a tool. It's not a tool that you download and use, because it's very specific to pretty much your use case. My implementation is 200 lines. So it's something that, it's going to take you much less to program it once you figure out how to use it than the savings you're going to get from using it. So that's how it goes. When you find a use for it, you probably have to write it yourself. Or maybe try to use my implementation, but my implementation is very specific to kind of narrowing down this range of identifiers. The one for GCC is cutting files in half. And the one